Hello, here's the final part of the 2011 Oxford Pat. This is the long physics question, the 20 marker. Let's see how we get on. An archer draws the string of her bow back a distance of 0.6 meters, holds it there with a force of 120 newtons before releasing an arrow of mass 20 grams. What is the speed of the arrow when it leaves the bow string, assuming that all the energy in the bow is imparted to the arrow? Okay. Well, we don't have a obvious, and we don't know how this bow behaves. This is part of the problem. When you draw the string back on a bow, you get a lot of things. You're stretching the string and you're bending the bow to some extent. If it starts relatively flat with a loose string, when you draw the string back, it also pulls the bow as well. So we're getting, it's not obvious what the force profile is going to be on that at all. So we're going to have to make some kind of assumption here. So let's assume this is already a pretty ropey looking question, unless this is what they're trying to pick apart. So we'll assume that all energy is in bow string, and it's a bit like an elastic band. Yeah, because we don't have an obvious model on this. Normally when they're doing these, they're saying, oh yeah, you've got a spring or you've got an elastic band, and they're not adding in other things that are moving. So let's go with that then. We'll assume that, in which case we're going to have conservation of energy. Our kinetic energy is going to be equal to the elastic potential energy, which in our model is going to be a half Fx, because the force is going to go from 0 up to 120. So we're averaging that. Our average force is 60 multiplied by the distance. Whether that is right or not, who knows? So 60 times 0.6 is going to be, it's going to be that. So that is equal to 36 joules, which is a half mv squared. So v squared is going to be 36 times, well, half of, or divided by the m. We've got, right, so 36 multiplied by 2 divided by 0.02 is 3, well, that's 100, isn't it? So 3600. So v is 60 meters per second. But that's all hinging on this assumption, which could well be wrong. Well, I mean, it is wrong that that's not how a lot of bow and arrows behave. But, maybe this one does. Maybe it's a completely rigid bow with an elastic band for the string. But that's what we're assuming. We're just going to have to go with that because it's the best thing that seems to be available. Right, in fact, the stored energy of the bow not only accelerates the arrow, but also the arms of the bow. And only a fraction h of the original stored energy is imparted to the arrow. If h is that, what's the actual speed of the arrow after, right? So we had 36 joules. So this is saying that a half mv squared is now going to be 25 times 36 multiplied by 36, so 25. So v squared is going to be 25 times 2 over 0.02, which is 2,500. So we've got now that v is 50 meters per second. Right. I mean, the fact that it's coming out with these really sensible numbers makes me think that maybe this is what they had intended when they created the question. They just haven't created the question very well, much like a lot of the questions in the previous parts of the paper. Right, now the archer aims at a target 50 meters away. How long will it take for the arrow to reach the target, assuming that the arrow does not slow down? Right, well, it's going 50 meters at 50 meters per second. So 1 second. Right, okay, easy enough. To account for the effects of gravity, estimate how far above the center of the target the archer must aim to ensure the arrow strikes the middle. So in 1 second, the arrow, because it's going to drop vertically, isn't it? Drops. So it's going to drop 5 meters vertically. So that's because the acceleration due to gravity is 10 meters per second squared. So in 1 second, we would have increased vertically the vertical velocity by 10 meters per second. So our average velocity is 5 meters per second multiplied by the time is 5 meters. So that's fine. So we want to therefore aim 5 meters above the center, 5 meters up. Right, so average velocity times time. If the arrow is brought to rest in a distance of 5 millimeters, what is the average force of the arrow strike? Right, so what do we estimate how far above? So this is, I assume, so they've aimed it upwards. What is the average force of the strike? Right, so we're going to be saying that, well, half mv squared. If they've aimed it so it's looped over like that, we're just going to have that is our energy. That's our energy transferred, which has got to be equal to our force times our distance. 5 times 10 to the minus 3. Our energy was 25, wasn't it? So 25 joules divided by 5 times 10 to the 3. So over 5 times 10 to the 3 equals F. So we'll say 5,000 newtons. Yeah. I don't know whether that's if we're aiming it like that. I suppose if you're aiming it flat, then we're going to get an extra bit of potential energy in there. So this is assuming aimed up 5 meters. So we're not getting any mg, we're not getting any GPE added to this from start to finish. So we'll go with that. This is a really unclear question. If the target has a mass of 5 kilograms, at what velocity is it thrown back by the arrow strike? Okay, right, so we've got conservation of momentum. So we've started off with the 20 grams at 50 meters per second, and that has got to be equal to 5.02, the mass of the arrow plus the target, multiplied by some velocity. So V is going to be 1 over 5.02. We're just trying to get this to two significant figures, I think, aren't we? So let's just say that's 0.2 anyway, 0.2 meters per second. Yeah, and that's the end of the question. Right, another disappointing question on this paper. The calculations are straightforward, but we've just got this air of unknown hanging over the whole thing, that we don't know. And we don't know how we're meant to be modeling the bow, so we're having to decide on that. It's not obvious out of all of the different permutations that have happened about whether they're firing it horizontally or slightly up in the air or not, as to what they've done when they fired it. I mean, it says if the arrow is brought to rest in that distance. Well, how did they fire the arrow? Upwards, downwards, sideways? I mean, it's, yeah. I mean, it feels like, I don't know, maybe with this paper, considering the first part of the paper with the maths was a lot more difficult than previous papers, then the physics was quite easy. And then for the written physics answers, there was quite a lot of ambiguity dumped in there. It makes me feel as though this paper has been constructed by a mathematician rather than a physicist. So maybe that's part of what the problem is. Anyway, I suppose not to worry. I mean, if you encounter papers like this when it seems a little bit weird, then writing down these assumptions, at least explain what you're doing as you're going through. Say what assumptions you're making. Whether it's being aimed up in the air, what model we're using for the bow and arrow, because at least if you say what you're doing, you can still get the full marks. Don't think that there's one definitive answer to these things that is the only way to say get 6 marks on this question. At least if you're saying what you're doing, you're acting like a physicist, they'll see that in your answer. Treat this like a conversation with the person who's going to be marking it. in which case you'll still be able to pick up the marks. So don't panic if you see these sort of things. You know, sometimes things just don't work out maybe as planned when they're constructing these questions. Anyway, that completes that 2011 year. It'll be interesting to see if the 2012 paper continues in this vein, or whether it reverts a little back to how things were in previous papers.